This video introduces us to the problem solving that goes along with colligative properties. We will just learn how to actually find the change in the freezing point and the change in the boiling point, so we will be able to calculate what temperature a solution will freeze and boil knowing the concentration. I would have a periodic table handy and a calculator handy. Now we're going to be solving some problems, and below the video I will share with you the actual problem sheets if you would like to take a look at or print them out prior to the video. So if you want to pause me and then take a look at that, otherwise just keep watching, of course. Okay, by the end of the video you will understand how to apply the colligative property equations just for these two colligative properties. I will demonstrate the types of problems that we will be asking you to solve this year. All right. So these have been developed experimentally. The equation for freezing point depression is often presented as delta TF equals that fancy little I, the Van Hoff factor, K subscript f lowercase m. All right, so what are all these different pieces of this equation? Well, in chemistry, usually a lowercase t indicates time. But I think the majority of chemists are just worried that you will misinterpret what this is. This should be a capital T, and some textbooks will show it as a capital T. This is the change. Remember, delta means change in. The change in the freezing temperature. That will be delivered by the solute in solution. Excuse me. It is not the new freezing point. It is the change in. So I think that's why we're using a lowercase t, and of course the little f is signifying that we're talking about freezing. Remember this cursive little fancy I. That's the Van Hoff factor. Now, colligative properties depend on the number of solute particles, the number. And so remember, this is what we evaluate per the formula of our solute. So remember, all covalent remain in molecular form if they're soluble. So for example, sucrose, C12H22O11, we know is soluble in water, but it does not dissociate or ionize. For every one solute particle, you get one solute particle. However, sodium chloride, now that ionizes in water to create separate sodium and chloride ions. And for every one of these, we get one sodium and one chloride. So the I value is 2 for sodium chloride, but only 1 for sucrose. Just to remind you, what if we had magnesium chloride? Well, this will dissociate into the magnesium ion and then 2 chloride ions. So the Van Hoff factor here is 3. Okay, so we're going to have to really be aware of what our solute is doing. This lowercase m, of course, is molality. And remember, molality is mole of solute per kilogram of solvent. All right, and what is this capital K, lowercase f? We refer to this as the mole freezing point constant. This has been experimentally determined per the solvent. So it's taking into account the specific heat of the solvent, the chemistry, and so on. Now these are constant values. They will be shared with you. So for example, on the first set of problems we're going to take a look at. Right at the top, I give you a table. I'm identifying solvents. We don't expect you to know any normal, remember, that means freezing at 1 atmosphere. So the freezing point of pure solvent, the only one you're expected to know, of course, is water. So these are other solvents. We're going to give you the freezing point of the pure solvent. Here is this molal freezing point constant. So if we're dealing with water, it's 1.86 degrees Celsius per molal. Ether, 1.79 degrees Celsius per molal. Okay, so these are degrees Celsius per molal, which of course allows us then to do the canceling that we need to just get degrees Celsius as your answer if needed. Okay, so this is what we apply for questions that ask us to find the change in the freezing point, or to solve for the concentration if we know the freezing point, maybe to find the new freezing point, and we'll do examples of all of those. Okay, boiling point elevation has a very similar equation. It's the change in your boiling point will equal that Van Hoff factor, KB times lowercase m. Okay, so what is different? Well, of course, this will be the change in the boiling point. Still Van Hoff factor, still molality, but this is the molal boiling point constant. It is still based upon the solvent, and it will also have the units of degrees Celsius per molality. Molality. All right. If we take a look, you of course have not only been shared freezing point data and the KF values, but also boiling point. The only boiling point you're expected to know is water. And then boiling point constants. Okay, notice the KF values are negative. Well, remember, a solution has a lower freezing point than the normal solvent. Now, KF values aren't always given as negative values. They can be. That just helps keep us straight when we're problem solving. But you may have to actually apply a sign change. These are positive because, of course, we are raising the boiling point. So if we're looking for change in, when you find the change in freezing point, because if your KF is negative, this will be negative because we're lowering based upon the pure solvent freezing point, where your delta TB values will be positive because you will be adding, you're increasing the boiling point when you have a solution. All right. Notice also that, they're different values if you're talking about freezing or if you're talking about boiling. So we want to make sure that, we know, okay, are we looking for boiling or are we looking for freezing? And then you're applying the correct value, of course. Now, it's much easier to change the freezing point than it is the boiling point. Of course, we understand the energetic differences between vaporizing and then freezing. And so we're going to have different values for the same solvent because of that. All right, well, the next video will actually dig into some problem solving. So we presented the equations, talked about what everything means. Okay, next we're going to get into some problems.